after pyruvate has been oxidized and has binded to coenzyme A, the job of coenzyme A is to feed it into the citric acid cycle. So you've got this 2-carbon compound that is basically the leftover of pyruvate, and it's attached to coenzyme A, and coenzyme A is going to transport it over here to a 4-carbon molecule. We call this 4-carbon molecule oxaloacetate, and coenzyme A is just going to drop it off. It's going to drop this 2-carbon molecule off, and it's going to drive away and go pick up another 2-carbon compound. It's going to drive away over here to go basically grab the other pyruvate that was just oxidized. But I just want to focus on what happens here. What happens here? The 2-carbon and the 4-carbon combined in order to produce a 6-carbon compound called citric acid. So this is called the citric acid cycle, or sometimes it's called the Krebs cycle. You can call it either one. So the Krebs or the citric acid cycle. And what happens next is a series of reactions that's going to heavily oxidize citric acid. So you can see I've got all of these buckets set up, ready to go. They are ready to strip high energy electrons away from citric acid. There's about 10 enzymes that are facilitating these reactions that I'm not showing. There is a lot of intermediates that are created, but we don't need to know the details. The important part here is that citric acid is going to be heavily oxidized. It's going to lose hydrogen, it's going to lose electrons, it's going to lose carbon dioxide. And the point of this process is to fill these buckets up. Fill them up with high energy electrons. And so that's exactly what's going to happen. There's going to be a bucket that swoops in, and it's going to get energized because it's going to strip away high energy electrons from citric acid. Now, when that happens, citric acid actually loses a carbon and 2 oxygens. It's going to lose a carbon dioxide. So a CO2 departs. And then another oxidation reaction happens. So this bucket comes by, swoops in, and scoops up some high energy electrons. And obviously a hydrogen goes with it. So it turns into NADH. Carbon dioxide is cut off. So we lose another CO2. So we're now looking at a 4-carbon molecule. Carbon dioxide departs. So we've got a 4-carbon molecule. It's not quite oxaloacetate yet. We still have a couple more oxidation reactions to go through. We have a couple more enzymes that need to work on the molecule and mold it, basically, back into oxaloacetate. So by the time we get to the bottom of the Krebs cycle, we're like halfway there, a little pop of energy is going to be released, and this pop of energy is actually going to be used to make ATP, one ATP molecule, through substrate level phosphorylation, similar to how we were making ATP when we were looking at glycolysis. This 4-carbon molecule is going to swoop around, and it's going to be oxidized by this bucket. I drew it in light blue because this bucket is technically not NAD+. It is a close molecular cousin called FAD. If I were to Google them and put them side by side, they would look very similar to each other. So the details aren't important. It's just another molecule that's capable of oxidizing this high energy carbon compound. And so just like with NAD+, FAD is going to swoop in, it's going to steal some electrons, it's going to get a hydrogen, so it's going to be reduced into FADH. And then finally, as it sort of swoops back around to the beginning, another NAD+ is going to come in. Another NAD+ is going to come in, and it's going to oxidize this 4-carbon molecule. It's going to strip away some of these high energy electrons. It's going to get a hydrogen with it as well. And finally, at this point, the 4-carbon molecule is regenerated back into oxaloacetate. Oxaloacetate is ready to go again. That's why it's called a cycle. It's sent through the cycle as starting as citric acid. It comes back out of the cycle as oxaloacetate, ready to turn into another citric acid just to start the process all over again. Now remember, 2 pyruvate molecules have entered. 2 pyruvate molecules have entered. So when this oxaloacetate swings back around, this coenzyme A has gone over and it's grabbed onto the other pyruvate that was oxidized as it came into the matrix. This other pyruvate that was oxidized. And this coenzyme A is going to bring this 2-carbon compound over. It's going to drop it off just like it did earlier, and the whole cycle repeats itself. The citric acid is sent through the cycle yet again, and we're just loading these buckets up. We're just loading these buckets up so that we have high energy electrons. We do get a little bit of ATP made, but that is not the primary objective of the Krebs cycle or the citric acid cycle. The primary objective, hopefully it's clear here, the primary objective is to create these buckets, NADH and FADH2. So you don't have to know the numbers, but I just want to make it clear what we have so far. So think about it. From glycolysis, how much NADH did we get? We got 2 NADH molecules, and we got 0 FADH2. After glycolysis, you have pyruvate, and pyruvate goes into the matrix and goes through this pyruvate oxidation. That's what's happening, or that's what was happening over here. It's basically preparing for entry into the citric acid cycle. Now, if you remember, for pyruvate oxidation, we get the production of 2 NADH. Right? When pyruvate is oxidized, a carbon dioxide leaves, and then the 2-carbon that's left over is fed into the citric acid cycle. So what's actually oxidizing it is NADH, or is NAD+, and that's going to turn it into NADH. So we get 2 NADH from pyruvate oxidation. We don't get any FADH2 production. And now, when we're looking at the citric acid cycle, so for every 1 turn, we get, well, let me just count. We get 1, 2, 3. Okay, we get 3 NADH, and we get 1 FADH2. But remember, 1 turn is from an oxidized pyruvate. But how many pyruvate molecules are coming in from glycolysis? 2. So there's actually 2 turns here. So by the time this is all said and done, we have 6 NADH and 2 FADH2. So hopefully these numbers make it clear that a major objective of the citric acid cycle is to crank out or to generate a whole bunch of these high energy electron buckets, strip these high energy electrons away. Let's not, I guess we can't neglect our ATP. We do get 2 ATP. We get 1 per turn, and so we're looking at 2 turns. So we get 2 ATP. We also get a net gain of 2 ATP from glycolysis. Overall, though, not much ATP has been made. We're going to see that in the last part, the part that actually needs oxygen. Remember, oxygen hasn't even come into the picture yet, other than we needed to know whether it was present. But oxygen really hasn't played a major role in any of this yet. Once we introduce oxygen into the picture, we get like 30 to 34 ATP being made. So the vast majority of ATP is going to come from the last part of this process.